I assure you that what you will observe is a vast wasteland.
Free and uncorrupted communication.
I'm just absolutely delighted to welcome you tonight for tonight's lecture. Tonight is the first of what we expect and hope will be an annual event of the Las Cumbres Observatory's lecture in astrophysics. It's an event that brings together the wonderful, famous Department of Physics at UCSB and the Museum of Natural History. You may not have known that physics is in fact part of natural history. This is your discovery tonight. This collaboration was started by Professor Lars Bilston, and I think he really deserves a round of applause for this brilliant insight. There's a great sponsor behind these lectures, but I will not go on. It is a great pleasure for me to introduce to you a person who will actually introduce the lectures themselves, as well as eventually the lecturer, Professor Crystal Martin, who is a specialist on the development of galaxies and galactic winds. Since coming to UCSB, the Department of Physics, and becoming a faculty member there, her research has been recognized by fellowships from the Packard Foundation and the Sloan Foundation. Please give a warm welcome to Professor Crystal Martin. Thank you.
UCSB consistently ranks as one of the top 10 physics programs in the nation for doing graduate study. And these graduate students, and actually many undergraduates as well, participate in a wide variety of research programs at UCSB with various faculty members, 3 of which are Nobel laureates. You may have encountered some of our outreach programs to local schools, particularly the Physics Circus, or attended one of the public lectures at our sister institution, the Kavli Institute for Theoretical Physics. Tonight, we're unveiling a new lecture program, the Las Cumbres Observatory Lectures, which we hope will be an annual event. And this is in a partnership with 2 other institutions that promote educational outreach, the museum and a new observatory in Santa Barbara. The Las Cumbres Global Telescope is a private scientific facility that's working in collaboration with UCSB. And it is my pleasure to introduce to you the observatory director, Wayne Rosie. Wayne was recently appointed as a senior fellow in astrophysics and engineering at UCSB. And prior to arriving in Santa Barbara, Wayne had a very illustrious career in the computer industry in Silicon Valley, particularly at Sun Microsystems and Apple Computer. Please welcome Wayne Rosie.
Thank you, Crystal. This is the first, I guess, coming out party, so to speak, for Las Cumbres Observatory in Santa Barbara, even though my wife and I have lived here now for almost 6 years. What we are trying to do is build a unique scientific institution that starts with the principle that you mix education and serious science together at a very fundamental level. And we have, I think, approximately 12 or 14 people who work for us here in Santa Barbara, and another 40 around the world. So this is quite a serious effort. And you'll be hearing from us, I guess, every year as we try to sponsor these lectures and begin to expand the education outreach of our institution. We're going to do a major project here with the museum and with the Sedgwick Preserve, which is a part of the UCSB preserve system out in the Santa Ynez Valley, to establish a great deal more in the way of astronomy education, not oriented necessarily to teach astronomy, but to teach critical thinking and to make kids and their parents and their teachers less afraid of technology and more willing to look at the world on a broad global way. So thank you for attending, and I hope you enjoyed the lecture.
And now on to the main event, looking for life in all the right places. Dr. Alan Dressler is famous for his studies of distant galaxies and the large-scale structure of the universe. Alan discovered that the environment of a galaxy influences what type of galaxy forms, and was instrumental in establishing that the type of galaxy has a strong influence on the size of the supermassive black hole that forms at its center, or perhaps vice versa. That's still a little bit unclear. Perhaps even more remarkable, though, than Alan's illustrious research record is his leadership role in the scientific community. Alan is a member of the National Academy of Sciences and played a key role in developing the telescope that will eventually replace the Hubble Space Telescope. He has most recently worked on defining a large NASA project that will be capable of finding Earth-like planets. Please welcome the first Las Cumbres Observatory Prize Lecturer, Alan Dressler.
Well, it's a pleasure to be here, and I want to express my gratitude to the University of California, Santa Barbara Physics Department for extending this honor to me, and to Mr. Rosing for endowing this lecture series and having the honor of being the first of these lectures. It's a great pleasure to be in Santa Barbara. It's been a wonderful 3 days, if busy, and I've enjoyed, I think, every minute of it. I think we got too many microphones. Now, this is the title page you get to see, because I guess I didn't put Las Cumbres lecture in big enough font, so, and maybe too low down. But you know, Earth was something I felt like highlighting, and maybe that was my mistake. Crystal has to mention that she and Don got married 2 months ago, and their first dance song in the reception was the country song "Looking for Love in All the Wrong Places." And when I was pressed for a title, I've got to have a title in 15 minutes, Tommaso Troy said, even though we had been planning this for 4 months. It was the only thing I could come up with, and I thought, actually, that's okay. But congratulations to them. I have no credentials to be giving this talk, as Crystal has very kindly pointed out. I'm a galaxy astronomer who was not trained or planning to do anything in this particular field. However, a series of serendipitous occurrences in 1993, when the Hubble Space Telescope was still broken, a number of astronomers were wondering what were we going to have to replace the Hubble, especially if they didn't manage to fix it. And they couldn't really get anybody to take the job of running the committee that would have to answer that question, given the dire straits we were all in, but me. And I was given a very powerful, nice committee, and we sat around through what at the beginning was quite a depressing situation, trying to imagine what telescopes we might build after the Hubble Space Telescope, which at that point had this very blurry vision and was the target of many jokes on Jay Leno, et cetera. And so disinterested in NASA was this particular committee that, in fact, they did not sponsor or listen to the committee at the beginning. But a wonderful thing happened in December '93. They fixed the telescope, and the pictures it sent back captivated everybody, the astronomers and the public, and I think everybody saw the power of telescopes in space really for the first time. And it has lived up to that promise ever since. So it changed the nature of our committee. Suddenly it was a wonderful thing to be doing, to imagine what would be following on. And NASA's attitude about space telescopes turned around 180 degrees. Space telescopes might actually be a really good thing, People were paying attention in a way maybe they hadn't since the moon landing, and it was a delight actually to serve on this committee. And so it happened that we started thinking about what would the future be like, maybe not just the next space telescope, but what could you do in space? What in particular, where was astronomy going? And maybe it was a sort of a group epiphany, but we realized that progress had been made in so many areas that now pointed to an ability to link up many things that happen in the universe and connect it to our being here, origins. And not just origins of everything, but our origins. You could draw a line, not from the Big Bang really, but from the first stars to form in the universe, which was about 500 million years after the Big Bang, through the formation of galaxies, planets around those galaxies, and the raw materials for life and the beginning of life. Clearly to us, we know that at least in this one place, that line was drawn. And we wondered, of course, whether this happened other places. And as scientists, we imagined that it probably had, but imagining was not good enough. We wanted to know. And we wondered, and I should point out that this line that I draw, I mean, maybe it sounds facile to say that there's a line from us, but there are a lot of things that are not along this line. There's no big black hole in our past. There's nothing, there are many exotic and fantastic things that happen in astrophysics that we see that didn't happen along the way to us, and if they did, we wouldn't be here. So there is a chain of things that had to happen, and those conditions must have existed other places. So what this slide tries to show is, it was a cover page for a report that we wrote, one that I quite like, which tried to convey that idea that from galaxies, which is in the upper right-hand corner, and this thing down here that looks like a galaxy, which is over the hand, is really the big birth of a solar system of planets. And then the chemistry and the DNA molecule, all these things in some way, and the comet bringing water, and the Earth planet here, all these things have a sort of commonality and an ancestry that makes it possible for life to be here and probably other places. So these two questions that we outlined in our report, how did we get here? Are we alone? The most simple way to put two of the most profound questions that human beings have ever dreamed up, and that they've had to live with as a dream for generation after generation and millennia. But we are a very honored generation, a very lucky generation, because we actually have within our grasp maybe to answer these questions. That is immensely exciting. The modern universe. This is the universe that began about 500 million years after the Big Bang. When the Big Bang happened, the universe was a very hot gas, rapidly expanding. It had particles not like atoms, but heavier things. It was very alien, very different from what we live in today. But sometime about 500 million years later, it cooled, it was expanding, and it became cool enough for gravity to bring matter together and form the first generation of stars. We don't know much about them. And those stars were collected into galaxy, or the next generation of stars were. And galaxies became the dominant sort of organizational unit in the universe. And this little picture in the corner here shows just a random sort of part of space. It's a place where there are a lot of galaxies together, but even all the things in the background are galaxies. When you look on the big scale of the universe, it's organized into galaxies. And inside galaxies, well, you have stars, you have gas and dust swirling around. In some places, stars are being born. Some places, stars have blown up, and that's a big part of the story. And all these things, it's happened slowly on our lifetime scale, so it looks static. But in fact, it's a very dynamic universe in which all these things are taking place. And then there are these other things that up until recently have not been the object of study other than the planets in our own solar system. Saturn, the Earth, just two representatives, a giant gas planet and a terrestrial planet, as it's called. We don't know whether such planets, we did not know whether such planets exist around other stars until very recently. So ironically, we could look all the way across the universe for billions and billions of light years and study galaxies and learn things about them, but not know whether the nearest star to us, or the nearest 100 stars, had planets like this. And we still don't know if they have planets like that. And that has been really a technical problem which we have finally become sophisticated enough to begin to deal with. What is this connection between galaxies and our being here? It's not obvious. A galaxy is a very large, unimaginably large structure with hundreds of billions of stars. I can't describe to you really how big it is. It takes 100,000 years for a beam of light to cross a galaxy, and that's imponderable for a human being. In this picture is a giant galaxy much like our own, but these are also giant galaxies just seen further away. And this little piece of sky photographed with the Hubble Space Telescope shows that galaxies dominate. And even the very faintest things here are galaxies. This one is a couple billion light years away from Earth and is seen as it looked a couple of billion years ago, because that's how long it took the light to get here. These smaller ones are maybe 6 or 7 billion light years away. The very distant things are maybe 10 billion light years away. And a lot of what I do, and Crystal and other people do, is trying to understand how galaxies have evolved through time, how they got to the way they are. And one of the great tools is to actually be able to look back in time. No other scientist, or anybody, I guess for that matter, gets to look back in time for real, and we do. So galaxies are the major structural building block, but that's a kind of a loose connection. But there's something that is much more fundamental. So as I said, the universe started out as gas. This is sort of what it looked like. This is a map of the world when it was sort of the universe all over around us, just like you see a map of the Earth, the sky. And galaxies formed, and that's the major structure of the universe, as I said. But there's this other item here, and that is that galaxies are the place where chemical evolution takes place. It's where all the heavy elements in the Earth and in our bodies were formed. And did galaxies not exist, the level of those heavy elements would not have risen to the point where planets could have formed and life could have begun, so we believe. They are giant reservoirs where the heavy elements have collected. Fusion is what goes on in the centers of stars. It's why they shine. This little cartoon, which I got off the web, shows a couple of heavy hydrogen atoms, the lightest element and the most common one. In the centers of stars, the temperatures are so high, the density so high, millions of degrees, things jam together, hitting with enormous force, that the nuclei of atoms fuse together. They can, and when they do, there's extra energy left over. When they're bound together, it's more efficient as a bound unit than it was when two separate pieces, and a tremendous amount of energy comes out. And the sun, I believe the statistic is, the sun converts a ton of hydrogen into helium every second, and that is why it shines. But this process has big implications for us, because it means it's the beginning of the building up of all the heavy chemical elements. By the way, this is something we're trying to learn how to do on Earth. The sun can do this because it weighs 1,000,000 times as much as the Earth and presses down, and it can hold in these gases at millions of degrees temperature. They don't get away, squeezes them down. And as I said, it converts a ton of this stuff into energy, sort of a minute, a second. But on Earth, we'd have a lot of trouble just containing 1 gram of material, and we're trying to build some very big machines that will do it. You can't build a solid structure that will be heated to 1,000,000 degrees, because of course it would melt, but you can use magnetic fields, and that's one way that people are trying to build fusion reactors. It would be a great solution to the energy crisis. It's proven to be a very elusive and difficult thing, but I do believe that eventually it will happen. Now, I searched the web for a friendly version of this plot. You would think that after all these years, I'm an old guy, somebody could have made a nice friendly version that doesn't look like the one that was on the wall of the 5th grade class that you were in. Because, it sort of makes you tense up. But this is it, and there is a lot of complexity hidden in this, and actually it's a good thing. The table of the elements. This is the story. Hydrogen and helium were the only things that were around at the beginning when the Big Bang had finished. Traces of other things, lithium and beryllium, but not much else. And the first thing a star does is, in its core, like the sun is doing right now, fuse the hydrogen that's there together to make more helium, until all the hydrogen has been converted to helium, and the whole thing in the center is helium. And at that point, it no longer has a store of energy to release, and all that weight that's pressing down on it, it can't support. So it begins to collapse, and in collapsing, it heats up until it gets even hotter, and the helium atoms start bumping into each other, and they begin to fuse into even heavier nuclei. And that's where we start to get carbon and nitrogen and oxygen. And these are things, of course, that are basic for life, basic for our own bodies. So the carbon, the nitrogen, and oxygen, also other things. I always like to point out calcium because it seems like it's so very vital. Not only my bones, but my teeth. You know, the teeth are right here. And well, I have to say that somebody told me recently that if you drink a glass of water, you share one molecule with Julius Caesar. That's how many molecules of water there are. So I hope he brushed his teeth a lot. But I can't think about that. But it upsets me. But in calcium, it's much better. Every single calcium atom that's in your bones and in your teeth was at the center of a star. That's where it came from. Every single one. As well as the carbon, the nitrogen, and oxygen. That is the most astonishing discovery of the 20th century, I think, in physics. I mean, there are a lot of candidates for it. But is there anything more remarkable than knowing that all the heavy elements that make up this Earth and ourselves and all the living creatures were once at the centers of stars, and they had to get out for us to be here? And that, of course, is a fundamental connection, and the thing that Carl Sagan used to say, we are all star stuff. Phosphorus, very important in chemistry of making our bodies work properly. All these things we could, kind of go through. But the Earth itself, later in the lives of some stars, they produce these really heavy things, the iron group elements, iron and nickel and cobalt. If you went down to the center of the Earth, you'd find that most of the mass in the Earth is these elements. And then floating on top of that, because it's much lighter material, is stuff like magnesium and silicon and aluminum and sulfur. That's the crust of the Earth. And then, of course, we're on top of that. So all these pieces coming together from the stars, and all coming from hydrogen and helium, the way it started. So galaxies are giant continents of billions of stars. They're a crucial part on the, way on the path to our existence, because every generation of stars is making these heavy elements and increasing the heavy element content. And if the universe was just a universe of stars without galaxies sort of holding them together, that material would just disperse and probably never reach the level that it has. It's about 1% of all the mass in the universe is in the heavy stuff. And in places like this, it's concentrated to make the Earth and us. So when you look at a galaxy, that's what's going on. These are factories. Every one of these is a star. They're cooking the heavy elements. And in that galaxy, there's gas getting ready to make young stars. They're being born here and here, and these stars evolve. How does the material get back out? Well, it depends on how massive the star is. The sun, which by strange coincidence has one solar mass. It's great the way that worked out. Will end its life in this very calm way. It will slowly blow out the envelope, all the outer layers, and there will be a lot of carbon and maybe nitrogen and oxygen, and that's how that material will get back into space. And then the remaining part of the sun will be a white dwarf, and it'll sort of cool into oblivion. That'll happen about 5 billion years ago. If it's 5 billion years from now, so you have plenty of time to settle your accounts. But far more dramatic is what happens to the really massive stars. Some of them are very massive, and some other exotic combinations in which stars blow up very dramatically, sort of completely disintegrating themselves back into space. This is a star going supernova in a galaxy, and for probably a period of a day, it is as bright as the entire galaxy. It's a very dramatic event. But it leaves all the stuff that it made, iron and other heavy elements, back in the intergalactic medium. So that's a part of the story we understand pretty well. We understand that it was really something completely learned in the 20th century, how stars go through this period of building up the heavy elements and how they return them into space, and then how that material collects and builds more of heavy elements until somehow they got up to the point where we could be here. We don't know much, we haven't known much about how stars are born, and that's beginning to change. And one of the reasons is because the process takes place almost in a cocoon. The gas and the dust is so dense in places where stars are forming that it's hard to look through it. Visible light does not penetrate. But as our technology has improved, we're able to look in the infrared, and the longer wavelength light in the infrared does manage to penetrate or to get out so that we can see what's going on inside. And that's making a big difference, a revolution. So we're seeing regions like this where the stars are forming and seeing these very strange outflows of material that are connected with the process of their birth. Just an example of that, this is the Spitzer telescope, which is now in space, doing fantastic science. And it is the most sensitive of the infrared telescopes. It's a gigantic cryogenic door with state-of-the-art infrared detectors. And one of the things it can do is look at a region like this. This is a picture taken with optical light, visible light. And that dark cloud is that shroud. It's that cocoon where the cradle of star birth is happening. And you can't see through it in optical light, but here's the very same picture taken in the infrared. So you begin to see what's happening to the star being born. See these two stars? Those are that. It's tilted a little bit, but it's the same field. So a lot is going to be learned from the Spitzer, and there's going to be an even more powerful telescope. As Crystal said, the successor to the Hubble Space Telescope, the James Webb Space Telescope, will be a very cold telescope so that it can look in the infrared, and it will be fantastic for looking at star birth. And it's going to be a big challenge. It's underway. I'll maybe talk a little bit about that more later. It's a consortium of Canadians, Europeans, Americans, being built now by Northrop Grumman and NASA Goddard Space Flight Center. Should be launched around 2013. Stars are born, but now we're getting to the story of how planets come about. We know that after this birth phase, this thick cocoon of material slowly gets blown away by the bright young star that has just formed. And we see, in many cases, what is left is a disk of material that is ice and dust and gas that is kind of the construction material from the star that's left over. And it's circulating in a disk because there's spin. And we believe these are the raw materials from which the planets will form. It's not easy to see this stuff. These pictures were taken by finding a way to block out the light of the star itself, because the star is enormously bright and it would just blind you. But it's that kind of a technique that people develop that allow them to see disks around some young stars. This new space telescope and the telescopes we're going to build on the ground in the future, we hope we'll be able to make observations that will show a process like this, where there's a dust and gas and ice disk that is collapsing in zones to make planets. There's a little planet here that is formed from the material that was in this part of the disk. That's the kind of process we expect to see. In our solar system, we know the process finished. Not going to talk much about it. With some giant planets that are called gas giants. They're much bigger than the Earth. The Earth is sort of a little dot down there. I think the Earth is quite a bit smaller than the red spot here. So these are things that probably have an iron core or something like that in the middle, or even a water core, but they in fact are mostly gas, mostly the primal material that's in the sun. They have a lot of methane and ammonia. They're probably not very promising places to live, but we're not exactly sure. Then there are things that are called ice giants. They are further out and are more dominated by methane ice, dry ice, water ice. But there are these terrestrial planets. 3, depending on your sort of definitions of things, there are 3 that are very similar in size, and they're all kind of close together. The Earth and Mars and Venus. Venus being shrouded in clouds. You can see the Earth is, you can see right down to the surface, and Mars has a very small atmosphere, and you can see right down to the surface. These are worlds where we believe, well, we know life started here, and we believe that life could have started on the other ones as well. Do they exist around other stars? We don't know, and that's what the journey is all about. But for the first time, we know that the giant planets do exist. So here's the layout of our solar system: Mercury, Venus, Earth, Mars, and then Jupiter and Saturn. They're all way out here. The first planets we found turned out to be gigantic planets like Jupiter, but as far in as Mercury, a big surprise. How could these giant planets that seem to form a very cold material wind up at the center? We're still not exactly sure, but people think that those planets form far from the star and then they spiral in. Some of them actually are eaten up by the star, and other ones sort of park themselves and remain close to the star. But this is a very different configuration than our own solar system, where Jupiter and Saturn are way out there and the terrestrial planets are inside. In this solar system, there may have been a few terrestrial planets, and they may have been wiped out as this big planet spiraled its way in. It would have dominated the gravity and probably would have taken those small planets with them. Well, those were very early observations. This is now a list, and even this one's out of date, showing the masses of the planets that have been found around other stars. I think there's a couple hundred now, and how far they are away from the star. Here's our location away from the sun, 1 astronomical unit. Another one of those funny coincidences. And here, we're finding Jupiters that are going further and further out until some of them are almost as far out as Jupiter in our system. And some of them are rather large planets, like 7 Jupiter masses. How are these things found? Well, it has to do with the application of the Doppler effect that everybody hears in real life when sirens go by and the pitch changes as something comes toward you and goes away. I have a little cartoon here, which I think is going to play, showing that if you have sources in astronomy that are radiating to you, giving out light, and you have a spectrum that has some demarked wavelengths in it, you see those lines. I have to show this again. The positions of those dark bands move around, and they move around in sort of a, they move in, they move out. A very normal sort of signature. This is what the graph of that looks like. The velocity is high, it's low, it's going toward us, then away from us, and the other star is doing the same thing. And look, this is what Butler and Paul Butler, Deborah Fisher, Steve Vogt, Jeff Marcy found when they started looking at motions of stars. The stars were moving back and forth, but there's no sign of another star because the planet that's doing the pulling is invisible. It's much too faint to see. So you only see one body moving around. And the speed at which it's moving, only like 40 meters a second. I think I can drive that fast without getting a ticket. And I'm not sure, actually. Is that true? No. This planet has got me in trouble. Okay. But their accuracy is to actually measure motions as small as a few meters a second. They can actually measure a star moving toward or away from us at a few meters a second, which I think I can even run that fast, maybe. And even though our Earth is moving around at 20 miles a second around in its orbit, the tug that it puts on the sun is very small. And even Jupiter, with its much bigger mass, only puts a tug like this on. So they had to overcome a lot of technical obstacles to measure with such great precision the motion of the star, but that's when they started discovering planets. And not only just single planets, but when you found something like this, while it did look like a simple curve, they began to realize that they were seeing the signal from more than one planet, which makes a sort of complicated pattern, and they could decompose it into 2 planets. And this one has a planet with a 14-year period. I guess this is 3 in the system, a 15-day, a 44-day, and a 14-year period. So this is a little solar system, sort of like ours. It's got 3 big planets. We're never going to find Earth-like planets that way, or at least not around stars like the sun, because the motion for a little planet like Earth that we would induce on the sun is just too small. We just don't have enough mass to drag it around very much. So we've got a plan now to find the first such telescope that will tell us whether there are planets of the size of our own. Is called Kepler, and it's something being built at NASA. And the idea here is to look at a star field where there are hundreds of thousands of stars and look at it repeatedly and wait for the time that the shadow, that a Earth-like planet transits across the face of the star. Because when it does that, it diminishes the light a very small amount, about 1/1000%, a very, very small amount, but you can measure that from space, or so we think. So this telescope, when it goes up, and it's only a few years off, will be monitoring this field repeatedly and comparing the brightnesses of the stars every night and looking for times when the star dims a little bit, and then a few days later, a day later, comes back. And that will be the sign. They will know by how deep that drop in the light output is and how rapid. They will know where the planet is and something about how massive it is, and they will know if it's an Earth-like world. And this particular mission is meant to be sensitive to planets in this sort of area on this plot, which is, this is the mass of the star, and this is the distance from the star, and this is called the habitable zone. This is the area from the star where water would be liquid on the surface. Inside this, the surface of the planet would be too hot, and you would boil the water away. Outside of this, it would be ice and it would freeze. But in this zone, the habitable zone, which is, of course, where we live, water can be liquid on the surface. So when this mission goes, and there's every reason to believe it will succeed, it will return a very important number. What is the fraction of stars that have a world like Earth? Sort of at the same distance from their star as we are. That will be a great accomplishment. And in fact, it's going to be really important to planning the next mission, because this is not good enough. This doesn't tell us much about it, just would tell us that they exist. However, if we don't find any in this, we can skip the next steps. Here's the next step. We want to see a planet around a star. And if we can see it, we can actually find out a lot about it. And I will tell you that shortly. But there is a problem. Here's the rub, as Shakespeare would say. The Earth is not really all that faint. If you were to go to the nearest star, and I don't recommend this, and look back with the Hubble Space Telescope, you have to take that with you, I'm sorry, you could see it. It's bright enough to be detected with this rather modest-sized telescope that we put in orbit. But there would be a problem. The sun would be shining in your eyes at about 1 billion times brighter. And that's, well, you know those searchlights that they used to use to open movie premieres, and I think they still take them to supermarkets, and those are 20,000 watts of light. It's kind of like having one of those things shined in your face, and somebody has a, well, fainter than this, but a little light, like, you know, striking a match or something like that, and holding it and said, "Do you see this?" Is a problem. You are blinded. And not only that, the Earth would be so close to that point of light that you would have to build a quite special telescope to have any hope of seeing that little point of light. So this example, this is a real case of a star and we will call it a failed star or giant planet that is sort of 100 times, it's like 20 times further away from its star than Jupiter is from ours. So it's very favorable. Nevertheless, they found a way to cut down the light of this star a lot, and already they've taken it down, I think, a factor of 1,000, and they can see that planet. But what we have to do is see a much greater contrast, and it's in here. The star is just a point. It's right in there. And this distance, how close it is, this is, you know, this is a little hard to think, but if you held a dime 10 miles away, that's sort of how close, you know, the center of the dime would be our star, and theirs would be the Earth. So there's, imagine, I don't know if you can imagine this, is sort of ridiculous thing, but there's a searchlight that all the light is concentrated into a point, and then, you know, it's the size of a dime and 10 miles away, and then there's this little planet next to it. Bright enough to be seen, except for the fact that you're being completely blinded. So as you can see, this might be a bit of a technical challenge. What makes this even worse is that light, although we talk about it as little packets of energy, little photons, so you might think you could just block the light of the star and look for the little light of the planet next door. Well, nature hasn't made that very easy. Light is a wave, and when it comes past any sort of edge, it creates a ring pattern like this. As a matter of fact, you can see this ring pattern in the outside of this image. It's called the diffraction pattern. The size of that pattern depends on how big the telescope is. The bigger the telescope, the smaller that gets. But this means that there's light not just in a point. Even though the star is very far away and really is just a point, light is scattered out right into where we want to look for our planet. So that's a problem. This sort of shows how that works. light is really a wave and somehow a particle too. And when waves go through a little spot or hit an edge that is sort of comparable in size to the wavelength of the light, it makes a new source of waves. So in a telescope, the edge of the telescope mirror and the supports for the telescope mirrors that hang over the telescope, all those things produce new sources of waves, and you get these patterns. And the patterns spread the light out in such a way that it's very difficult to see what you want to see. I'm sorry that this animates so badly, and it's really good on the internet, and then it sort of lurches around. What this is supposed to show is waves can be made to add up in a way that they get bigger. So there are two waves here that have been summed, and sometimes they get twice the amplitude, and for brief periods of time, when they're out of phase with each other, they cancel each other. That's when this thing goes flat. As you can see, it goes flat and then it gets tall. That is what we're going to use to our advantage. The fact that the light is a wave means that maybe we can, in fact, use it to our advantage and find. So here's an example. This is what we would call a standing wave. The light is intense. It goes positive and negative, but that's all average. That's a lot of power. The light is intense here, but here, in this one little spot, it's zero. Somehow we've managed to take light and cancel it with its opposite signal and find a place where it's dark. Now, how is that going to be useful? I don't know if anybody ever did this in physics class, but you get these little trays of water and you have these little things that bob up and down. It makes waves. It's very nice. What is shown here is a source of waves next to a wall, which generates waves reflecting back. And you see, in this case, they've phased things so that the waves add up, and the amplitude here is twice as great. The waves are adding together constructively. And on this side, they've weighted an extra half a wave so that the waves are out of phase, and the waves are canceling. So there's this nice dark zone there where it's all very quiet. You see where this is going. We want to get that star. We want to take its light and somehow cancel it with itself so that we can get rid of it. But then the little planet that's next door, we want to keep that in phase so we can see it. And that's what the game is all about. Now, there are no walls up in space to which to bounce the signal. So this is more realistic. If we took the light from the star, for example, and collected it in two places, with two telescopes, then we would have places, zones, where we would have a nulling signal, where the waves would not be high and the intensity would be low. So that's kind of the basic idea. Find ways to get light to work to our advantage, to cancel itself for the star. So I want to tell you a little bit about doing this with a ground-based telescope. It sounds like we're getting there, but it turns out that this diffraction type of size light that you could get with a telescope, well, you don't even do that well from the ground for another reason, and that is that if the light were coming in nice parallel waves like I just showed you, and it was collected by a telescope, you get this nice bright spike, and there are those waves that we saw, the diffraction pattern, but it isn't like that. The atmosphere is a destroyer, and it takes the light and it makes it all wiggly and out of shape because the atmosphere has cells of different temperature and density sort of floating in it, and they act like lenses and they move the light around. Not much, but enough that when you go to a telescope, if you looked at the images closely, they look sort of like this, and they're changing rapidly as you're looking up in the sky. It's what astronomers call seeing, and that gives you an image that maybe looks, this is awfully bad, but that's okay. Something like that. So you're not even getting down to the point where you can apply these techniques to get light to interfere. You've got a problem. But we're working on this. A lot of telescopes now have something called adaptive optics, where they try to sense what the atmosphere is doing and cancel it. Again, we're trying to use the nature of light. Maybe we can find out what the distortions are and then feed them back in and straighten things out. I have these noise-canceling headphones that I take on the airplane, and that's really what they do. They listen to the sounds in the airplane, and very quickly they produce the out-of-phase equivalent of it and correct things, and it's quiet. So here, at the Keck Observatory that the astronomers at the University of California, Santa Barbara have access to are examples of images taken with this adaptive optics on and off. And this is Uranus, and these little spots come clearly into view. You can't see them here because the image isn't really sharp. Here's a star field that looks like, you can see this myself. This is without the adaptive optics, and I believe this is with it turned on, and here's another example here. It's very promising, and when you combine that, okay, here's another example. The way that the University of Arizona is doing it is they make a mirror that has a lot of adjustments up and down, and they sense what the atmosphere is doing, and then they correct to undo what the atmosphere did. And so with the adaptive optics off, the star is a kind of a big blur. When you turn it on, you've got like a diffraction limited image again. So good. There it went from a big blob, and now we're looking more like what we needed. So this is a good step. Now you combine that with the greatest telescopes in the world that people are trying to build, and maybe you're getting somewhere. This is a 30-meter telescope that the University of California and Caltech and the national observatories and Canada are trying to build, and it's an enormous project, enormous construction. This is an earlier observatory of the same size. And you see they made a mess of it. We hope they'll do better this time. It would be nice to actually talk about this for a long time, but the point is a big telescope like this has fantastically sharp images, especially if you can use this adaptive optics that gets rid of the atmosphere. And so there is great excitement about trying to use this to find planets and to use techniques that I will not go into right here that allow you to knock down that star. But unfortunately, because of the atmosphere, we can't do everything we want to do from the ground. This is the limit in sensitivity. Okay, so what's plotted here? Again, distance from the star. This is kind of the zone where we'd be looking for an Earth if we were looking for at a neighbor star. And this is the contrast that you need to see a planet. And the bigger planets, you need less contrast, so you only need about 100,000 to 1. And the fainter the planets get, it gets to 1 billion to 1, and you get into trouble. So here are the terrestrial planets down here. That's where they're going to sit in this plot. Each one of these is a pretend planet. And these are the giant planets in here. And unfortunately, even with a great big telescope like the 30-meter telescope, this is as faint as you can go. So you can look at these things. And these are younger planets that are still glowing of their own selves. They're not just reflecting light, but actually glowing. And these are very interesting things to study, but they're not going to get us to the planets that we see in our solar system. And the reason is that try as we might to correct this, we can only put so much light back. You know, it's a Humpty Dumpty story. There's still this little light sort of leaking around the side, and we're trying to reach a contrast of 1 billion or 10 million. And that's so hard that even a little light leaking out, we just can't fix what the atmosphere has done that well. And that's why we go into space. The terrestrial planet finder, this was what it was first drawn to look like. 4 telescopes that would be linked together, sending their light to combine in this craft here in a way that would allow, so you would see a pattern like that. You would look at a bright star that you wanted to look for planets, and you would see a wave pattern like this, and you would phase these, as we were talking about, so that the light would cancel crest to trough to make it go dark. Get a signal like that, a null. It's called a nulling interferometer. Now, here's the picture you would get out of such a thing. You have to operate this thing for a day and move it around, rotate it and things, but when you're done, the center part is gone. It's not white like this. It's just that there's no signal there because we nulled it out. And these little blobs are planets around that star. So it's a little solar system, and if you come back next week, they will have moved some. They're going around the star. You've detected planets. And this telescope probably if they were telescopes, each of these were something like, I don't know, 13, 14 feet across, which is good size, and you had 3 or 4 of them, you could detect an Earth around these, say, nearest 100 stars. So it was great excitement about this when we started talking about it, and I think at the beginning people thought we should rush ahead and build this right away. It's difficult. These spacecraft are free-floating because they need to be separated from each other quite a way. So originally they thought they'd put them on a boom, but in fact the boom kind of moves around too much. I mean, the precision here we're talking about is so great that we have to hold these to respect to each other to a wavelength of light, and I believe that's pretty small. And it's better to just let them drift into space without tugging on each other, and so they have to be free flyers, and they will fly in formation. And then lasers will make sure that they stay the right distance from each other, and they will keep their distances and move little mirrors and things, and it can all be done. But it's all new, and it's a kind of technology that we're probably 10 or maybe even 15 years from making work. But it should work, and it should be the beginning of very big instruments for finding planets. There's another version of the terrestrial planet finder which has come up called the Coronagraph, which does not use separated spacecraft. That one, by the way, works in the infrared, the one we were just looking at, which makes the job a little easier because the contrast of the Earth-like planet with the star is about 10 million instead of 1 billion. That's better. And the visible one has to do better, but it doesn't need, because the wavelength of light is shorter, it doesn't need such a big structure because it has a finer point size. And so it is a telescope, which is a kind of a elliptical mirror that is very big, like 25 feet long and maybe 10 feet across, that is more like a traditional telescope in which they play various games with the light as it comes in to get it to cancel. They pass part of it, they turn it around and add it up so that at the end you have this sort of diffraction pattern becomes something like this, and there's an area where you have nulled out this signal, and what used to be the bright star in the middle now looks like this, and there's the planet, which you couldn't see before because it was swamped and it was in there and it was so faint. Now you're down many factors of 10, hundreds of thousands in intensity, and you can see that planet and you can watch it move and everything. So these are the paths that we imagine to finding an Earth-like world. But there's much more to the story than that. So first we talked about finding them just by looking for their light. They're transiting a star and seeing the star dim a little bit. Now we've talked about actually seeing the light from those planets. But really astronomy is more than just seeing things. It's about taking the light and spreading it out into spectra and figuring out what's going on. In this particular case, what you can learn about a world is very exciting. So we come back to the question of life. When I was young, the prominent theory about life was what I call the Goldilocks theorem, that life was very special on Earth because it wasn't too hot here, it wasn't too cold here, it was just right, we were the right distance from the sun, and we had the right amount of water, and everything was just perfect. And people wondered whether these were very special circumstances and that we might not find life to be very abundant. But in the late 1970s, a discovery was made on Earth that changed, I think, a lot of thinking. They found that in the very bottoms of the ocean floor, at depths of 1 or 2 miles, there were volcanic vents. There were places where very hot gases and lava were coming out, superheating the water. And you might think that those areas would be devoid of life, but far from it. They were oases where there were complex forms of life, like these tube worms. I mean, they were just crowded with life. No sunlight ever penetrated down there. We didn't get to see these things until we built these submersible submarines that could go down and shine lights on them. But here were forms of light that had nothing to do with sunlight. They were hardly in what we would call hospitable conditions, and they could have been there whether the planet was 4 times further away from the sun or even closer, because it didn't have anything to do with the sun. In fact, the sun doesn't penetrate down there. Very, very interesting. And then, to boot, they found out that life had adapted itself very well down there. This is a little diagram that people who work in this field call the tree of life. And we can't go into great detail about that, but we're on the end of this. There's plants and there's human beings and other complex forms are at the end of one of these trees. And as you go back on a branch, you get to simpler and simpler organisms, and most of these are just one-cell creatures. So these all share a kind of DNA, RNA structure that makes them family members. Eukarya, it's called, the Eukarya family. Then there's a family that we call bacteria. They all share a common, these are all single cell. They all share some common features, and we know that they are related to each other and arose in sort of common evolution. But this batch, Archaea, was not known to exist until these environments were looked at. And a whole third family of life was discovered down at the ocean trenches. And these creatures could never live on the surface of the Earth. They would find it just unbearable. They need very, very hot conditions. That's the way they do their chemistry, their metabolism. That's the way they live. And they're actually called thermophiles for that reason. They are lovers of heat. So people started to think, wow, maybe life started this way. Maybe it didn't have anything to do with the sun and hospitable conditions. And if you have water and you have heat, well, you always have the carbon compounds and things. That's very common stuff, we believe. When any planet like the Earth would be built, you'd have a lot of hydrocarbons around, probably. So maybe these conditions weren't special at all, and life could have arisen any place you could form a planet. And I think people began to believe that maybe, in fact, life was very common. Now, during this time, we started to learn more about Mars and this key ingredient of water. I mean, I think that's one thing that everybody agrees. It sounds kind of chauvinistic to think that life would arise in conditions just like we have, but it's a good place to start because it's a little hard to imagine other things we don't know. And water is really a remarkable substance. It is a tremendous solvent. All these organic compounds just dissolve in it beautifully, and we believe that life began with some sort of ability of molecules to come into proximity with each other and try lots of different things. And there are other solvents that are perhaps as good but not as common. You wouldn't expect to find great lakes of ethanol and alcohol, but it's something that we believe water is common and probably exists on other worlds. And lo and behold, Mars is just such a world. When the Mars Global Surveyor went into orbit around Mars with a camera that had much higher resolution than anything had ever been before, they found these river valleys where it was clear that water had flowed, and water had flowed for a long time. You could see sedimentary layers there. So just as in the Grand Canyon, the water had cut down through the surface and revealed layers that had probably been the bottom of a lake. Usually when you see layers like that, it's because that over time there was a lake there and sediment just accumulated, made layer and layer and layer, and then something cuts through it and reveals all those layers. Sedimentary rock. One way they know that this is probably was a feature where water flowed for a long time is this river has a meander in it. I must admit I'm having a little trouble seeing it. I guess it's this one up here. The river, oh, here it is. The river apparently used to go around the long way and finally got tired of that and cut its way through. And you see this on all big rivers on Earth, like the Mississippi has lots of meanders. So that probably meant it was a long-lived feature. So Mars, we believe, had quite a bit of water for about maybe 1 billion years, and nobody's really sure. But these great missions that are going on at JPL have discovered fantastic things. More recently, it was discovered that there may be water on Mars in modern times, although not on the surface in any common way. How do they know that? Well, they found these features in cliffs, these little rivulets coming down, and these areas are all very young. They know that because there are no craters from rocks and things falling into Mars. And Mars is any place where the surface of Mars is old. There are lots of pockmarks from craters. It doesn't have an atmosphere as thick as ours, so every little rock that's the size of a basketball makes a good-sized crater. This is new, I was going to say new Earth. This is new Mars. This is material that is relatively recent, like 1 million years old or less, but that's a lot younger than 1 billion years old. And it's not pockmarked. And here are trails of water that have been come down. So people believe that for some unknown reason, there is water beneath the surface, and sometimes it sort of geysers out and runs down the cliffs. It doesn't survive for very long in this condition because the vapor pressure is so low on Mars that it sort of evaporates away. But it apparently survived long enough to, and it happened many times, to cut these channels. What's sort of exciting about that? Two things. One is, I say it could be 1 million years old. It also could be 100 years old, this area. You don't really know when this happened. We just know it's within 1 million years. So that's kind of interesting. This could be a very recent phenomenon. It could be a very current phenomenon. And the other thing is it implies there's water under the surface. So even though the surface of Mars is inhospitable today, it's a very alkaline surface and be a good place to sterilize stuff, not to grow things. But under the surface there are water, and we know where there's water and heat, and there may be some residual heat left over. Maybe there's some sort of hidden geysers there. There may be life. Life could have started there, and as the planet cooled down and the atmosphere escaped into space, maybe life retreated below the surface. There was tremendous excitement back in, I think it was 95, when a rock that was found in Antarctica and identified as being from Mars, called the Allen Hills meteorite, was found to have some little structures in it that were, to some people, reminiscent of a living structure. How do you know this rock comes from Mars? It turns out that trapped in the rock are little pockets of gas, and we have machines now that assay what the composition of the gas is, and it's a perfect match to the Martian atmosphere, and nothing like the Earth and any of the other bodies. So, believe it or not, when a big rock comes in sometimes, maybe the size of a car, a Volkswagen, smashes into Mars, it actually can blast some rocks back into space with enough force that they can go into orbit and then kind of sweep around and get caught in the Earth. And the best place to go look for rocks like this is in Antarctica, because generally it's all white and covered with snow, and you can walk around, and any rocks you find in Antarctica came from space. It's really true. And these guys go in these big, suits, and they go looking for rocks, and most of them come from the moon, but some of them come from Mars, I think a few percent. So there was a lot of excitement by that, and in fact there were this was in that rock, and people said, oh my gosh, it looks like a worm, and got very excited. And it created a wonderfully exemplary scientific discussion, which I had the pleasure of listening to a lot of the debate at the time, which was very high-minded, very strained, very hard, and it was great to see the scientific community work through this. But the eventual conclusion was that people did not believe that this was, in fact, signs of life, and that those structures, although they looked like sort of our idea of what living creatures might be, do arise naturally when there's water around, and could have built up and they're not the fossils probably of living organisms. It means that we have to, if we're going to find life this way, it's not going to be the structure that's going to tip it off. We're going to have to take a little structure like that and put it into one of these machines that can kind of decompose it into its molecules, and we got to look for things that could be in the byproducts of life. Let us call it the waste products of life. Life has a habit of leaving waste products behind it, which is why things crawl away. And we will probably find someday, if we are lucky enough to find evidence of life on Mars, the signs that metabolism was in place and that material was left behind as this little creature, and it might be a very little creature, sort of scurried its way along for new food and left behind the waste. And this is not the way to do it, just looking at the structure. However, there's been much progress in looking for water on Mars. These are these two rovers that went down and landed, I guess, 2 years ago on the 4th of July. One of them was the 4th of July, I think. And the Spirit rover, and what was the other? Somebody knew. This was, Spirit wound up in a very interesting place, and they crawled for a long way, and they found what they were looking for, which were, I don't really understand this myself, but in this embankment here, which they thought, because again of sedimentary layers, could have been a lake bed, they found some deposits of minerals that are found in lakes on Earth. They're little balls of mineral that form in water. So this was considered, I think is considered, convincing evidence that this was a catch basin of water. And now you can actually see maps of Mars where they sort of hypothesized that there was a big sea here and maybe some channels and rivers flowing out. It's not the only place where there's water in the solar system. This is very exciting. The moons surrounding Jupiter, there are 4 large moons, and 3 of them have these remarkable surfaces. I mean, people saw this stuff at JPL, the scientists, they were just agog. No surface of a planet or anything had looked like this, and they had a very hard time. The geologists were completely stumped for a while. What was this? But they figured it out. This is Europa. These are ice flows. They are chunks of ice basically banging into each other. And they are ice flows of probably water ice, almost certainly. And they are flowing on something which is probably liquid water. For some of you, it may surprise you that there could be liquid water so far out in the solar system. It is really cold there. It is 100 degrees below zero. But it is Jupiter itself that makes this possible. Jupiter has a tremendous gravitational pull and tidal pull, and it strains these poor little moons and sort of stretches them in and out and in and out, and that keeps them very warm inside. So there's a source of heat that's actually coming from the orbit of the moon. You know, we do the same thing to we raise tides on the moon, and we're causing heating of the moon, and it raises tides on Earth, which cause the water to kind of change level. But here it's really quite drastic, and it means that the temperatures in those worlds. We know this because Io, the one moon you don't see on this picture, is so close that it has volcanoes coming out of it. And it's practically a molten world on the top layers. So there's probably seas, maybe in all 3 of these bodies, but Europa is a prime candidate for a world that has had water for billions of years underneath this ice layer. And it would be fantastic to be able to go there and see whether, in fact, there are organisms, simple ones, complex ones, swimming around in that ocean. But there are missions being planned, it's difficult, that can at least, through various ways, sensing from above Europa, how deep the ocean might be, where it might start, where the water, liquid water is, how deep it would be, maybe some other things about the circulation pattern and all. It may be a long time before we go there and drill down, but we may learn quite a lot about it. And I actually wanted to show this, that one of the things that this 30-meter telescope can do with this adaptive optics, it may not be able to find an Earth-like world, but it can look at Europa sort of as often as they can get time on the telescope to do it, with very sharp picture, much sharper than it sort of looks on this projection, forgive me. And you can look at all those little ice flow things, and they can watch to see how they change. We don't have a continuous space presence to watch it and watch it and watch it anymore. And what scientists want to see is whether water gushes out from time to time and freezes, and that's why these structures look the way they do. So that would, in fact, itself be a very great clue as to what's going on in the ocean below. Back to the TPF. Looking for life. We know how we might do it on Mars and maybe even someday in the moons of Jupiter, but fortunately we can go further than that. The Terrestrial Planet Finder, if it finds such a world, if it is willing and patient to sit there and gather the light from this little Earth-like world for many weeks, sometimes months, it can produce a spectrum where we have the wavelength of light, the color of light versus the intensity. And these are the spectra of 3 of the worlds we know well, Venus, Earth, and Mars. You notice that they all share a very strong signature. These are caused by CO2 molecules in the atmosphere of all 3 worlds. An Earth-sized world, the main thing it has in its atmosphere is carbon dioxide. If it were bigger than the Earth, it keeps all these light gases, methane and ammonia, and that's why the Jupiter worlds look like they do, and it's a very different signature. If it's much less massive than the Earth, it has no atmosphere at all. It can't hold it. It doesn't have the gravity. So only in this relatively limited range of mass, of size, do you see this carbon dioxide. So if we saw that in the spectrum, we took the light and made a plot like that. Actually, it's kind of cruder than that. This is what we'd actually expect to see from this instrument. But there's that CO2 feature, and that would tell us, yes, this is a world like Earth. This is a a dip in the light that is caused by water, and it means there are clouds. It only shows up on Earth. Guess what? There are water clouds in our atmosphere, which is why it rains and why there's water on the surface in equilibrium with that. And you don't see that on either of the other worlds, and you don't see oxygen, ozone, in any of the other worlds. And that is the most exciting one at all, because that oxygen is there because of life on Earth. Respiration of bacteria and of plants puts the oxygen in the atmosphere. And if it didn't, in fairly short order, maybe millions of years, hundreds of millions of years, but in much less than the age of the Earth, that oxygen would be absorbed into the rocks. You know, things burn, oxidation, very, very strong chemical process, and it wouldn't stick around. That signature would disappear if life on Earth disappeared. So if we saw that in another world, we'd have a very strong clue that there was living organisms on that planet. This is what the Terrestrial Planet Finder interferometer, the one that works in the infrared, will do. In the visible, you have more complex but also less strong features, so it's a bit of a trade-off. But this shows a spectrum of Mars, where again there's a CO2 feature that's quite strong but not much else. One of these is Earth here. And again, you see water and lines of oxygen and such. So in both the Terrestrial Planet Finder that works in the visible and the one that works in the infrared, you have diagnostics which tell you whether there's water there, whether there might be life. A difference is that the infrared one is actually sensing the atmosphere, light that's coming from the atmosphere of the planet. The visible light version is actually getting light reflected off the surface. It'd be nice to know both things, and people who work in this field hope that someday both kinds of things will get built. Now, I said that oxygen, in fact, is a dead giveaway for life, and it probably is, although people were skeptical that maybe they could get it some natural way with volcanoes and such, and it's a matter of some scientific debate. But it's also important to remember that oxygen has not always been in the atmosphere of Earth. This is time before the present, so it's a few billion years leading to us today. And this is the oxygen level, and it doesn't matter what the scale is, but it's much higher now than it was in the past. And this is that time when the first aerobic bacteria arose on Earth and started filling the atmosphere with oxygen. This was the greatest poisoning episode in the history of the planet, and some very large fraction of the species that existed at that time died because they were oxidized. It's very corrosive, and they were not prepared for this. But what it made possible, apparently, it was possible with oxygen in the atmosphere for multi-cell creatures, complicated creatures to evolve, because oxygen is such an efficient oxidant that you could bring it inside a collection of cells and do metabolism and respiration well inside the organism. Whereas with this sort of weaker form of metabolism that existed before there was oxygen in the atmosphere, almost it seems like the cells had to be in contact with the atmosphere, and therefore you couldn't build anything like us, animals, plants, things that were more complicated. At least that's what some people think. So we do have to be prepared to look for other signatures, and there's methane and ammonia, and to look for gases that are, people say, out of equilibrium, more or less than we would expect if it was just inorganic chemistry going on. And this is, of course, the object of a lot of interesting study. I wanted to show you sort of the first, this is a very nice little tribute to Carl Sagan that he made, the first such measurements of looking back at Earth, just to show that you could see these features in the Earth's spectrum. On the Galileo satellite, they put out a little spectrometer and looked back, and you could see things, these features on Earth. We'll never, well, it'll be a long time before we ever get spectra that are as clean and high quality as this, but in fact you can see all kinds of wonderful things. I'm going to come back to that in a second. If you could get very good spectra, the terrestrial planet finders I've talked about are the first attempt, and will answer basic questions. But there is a fantastic amount of information to be seen from worlds that are light years away without ever visiting them. These are spectra, and the infrared again, of different kinds of clouds in the atmosphere. And you could determine between different composition clouds and different heights and learn something about the structure. That's sort of interesting, but what's actually more interesting, in the visible wavelength, where you're actually looking at the surface, the reflected light can tell you fantastic things about what's going on. This signature here, a big absorption of light and then something that's almost 100% reflective, I believe it's very, very reflective, is from the chlorophyll molecule that's in leaves in all sort of plants. Of course, it's right around the peak of light coming from the sun, because what the plant is trying to do is absorb the energy from the sun and do its chemistry. But if it absorbed all the light from the sun, it would burn up. It would get too hot. So the molecule has been evolved over time to be very reflective further out in the red. So the chlorophyll molecule looks very dark at some colors, and then it reflects light back further in the red. It's a very distinctive signature, and no inorganic molecule that we know of would have anything like that. So you can imagine looking, and by the way, here's, looking, this was, I believe, looking at the Amazon basin, and it's looking at a desert. You don't see it. There aren't any trees there. I thought this was the Amazon, but it says conifer forest. Anyway, you don't see it. And this may actually it's not from that mission. It's probably things they've done recently. But the point is, you might not expect to see chlorophyll in another world because it had a different biogenesis and a different evolution. But this kind of a molecule, this kind of a signature would be unmistakable. And it might be the case that you'd expect the same sort of solution in a world like that. Well, you can get very carried away, which is a wonderful thing. And you can start writing down all the things that can go on in the atmosphere, all the chemical reactions, all the things that volcanoes put in. You can imagine looking at seasons, because as you would be looking at one side of the planet and the plants would come back to life. You could see this on Earth if you had a sensitive enough telescope looking back. You could see the greening up on one side and then the winter season. You could see cycles of the sun. You could see all kinds of things and learn in very great detail what's going on. Now, I pulled a fast one on you. It's not going to be easy, because to do something like that would take not just this little terrestrial planet finder, but this is something you might imagine, a flotilla of 40-meter telescopes, so huge things like bigger than this room, with miles apart from each other, flying in perfect formation, sending their beams to one combining spacecraft to do something like collecting the light. And that's sort of the next phase. It's called Life Finder, and it's something that is probably half a century in the future, maybe 30, 40, 50 years. But it's wonderful to know that not only would you do this next step, but you know what you want to do next if the technology comes up to the task. You know that you want to put lots of collecting area into space and learn how to put it all together and look for great detail at what's happening on these worlds. It's even possible you might want to make an image of a world. That's the most difficult thing of all. What's the prospect for doing that? Well, this is the Hubble Space Telescope. It's a grand machine that was built much like an Earth-like telescope that was put into space. A big can, a mirror down here, a mirror cover, and some solar cells. The next telescope, the James Webb Space Telescope, you can see we are progressing to different things, has a mirror made of segments that unfold. It is out uncovered. It has to become very cold itself, and it has a big sunshade which it hides behind a big it's about the size of a tennis court. It's a very different kind of telescope, and it's moving us along the way to lighter materials, more modern sort of engineering. It's not a big can anymore. This is the direction we'd have to go. This is a mirror for the James Webb Space Telescope, and you see it is much bigger than the Hubble. The Hubble mirror is sort of like that big. And this is sort of just the beginning. I think I've got a little picture here. This is what the James Webb Space Telescope became, and this is this 30-meter telescope we're talking about. So we'd have to be able to launch things this big into space, which is very far beyond our capability. But people are thinking about it. They're thinking about novel ways to make telescopes that look really nothing like the telescopes we have today, frameworks in which you can stretch sheets of sort of mylar-like material, reflective material, and to stretch it in such ways that it achieves the proper curves. So this telescope has, these look like they're flat surfaces, but the way the struts are made, they actually introduce curves into the sheets, and the two surfaces together make a telescope. So the light comes in, hits one, bounces off the other, and then a third mirror here. And you can imagine this being very big. I believe that is supposed to be compared to, well, it's one of our present-day spacecraft. So this is what one of those elements in that huge array might look like. And as they like to put it in engineering terms, you need to get the weight of the mirror down to 1 square meter of it would only weigh a few pounds. Instead of today, it would be 100 pounds. That's what's going to make such a thing practical. These are big dreams, but you have to remember what aviation looked like in 1905 and where it is today, and think, gee, maybe in a century you can do a lot. That's the road for Terrestrial Planet Finder. Now, somebody should ask, are there other ways to look for life? And there is. The search for extraterrestrial intelligence is a very ambitious, well, that's not the half of it. It's a very bold move to try to find communications from intelligent species. And it has a wonderful sponsor. Paul Allen from Microsoft has taken this project to his heart and is funding, along with some other people, what will be an array of satellites. These are the dishes that are going in. I guess there's a person here standing next to one of them. They're 6 meter. They're basically sort of like satellite dishes that we use for receiving television signals, except they've expanded the concept and done it very inexpensively. This will be much more powerful at listening of all different frequencies across the radio spectrum, and they have very sophisticated ways to listen for signals that might be patterned and non-natural, that might be intelligent. It is a gamble, in a sense, that makes any lottery on Earth look like a sure thing. But the payoff is so phenomenal that you can't imagine not trying. Because what if it really is the case that somebody, has been around and has set up this array of communication devices, and it's been broadcasting to us, waiting for us to tune in? We'd feel pretty stupid if we found that out centuries from now. So it's good that there are people with more guts than me who want to do this, committing themselves to a life of science which is difficult and they know is unlikely to give a positive result, but if it does, it'll change the world. It will change the world. So I applaud them. And maybe, while this goes on and the other goes on, we'll see what happens. But it would be a shame not to look for this, a single cell, one of nature's great creations. And you won't find them communicating by radio waves or much of anything else, I'm afraid. And the complexity in this single cell just dwarfs anything that I've shown you from astronomy tonight. Stars, galaxies, planets. It's what nature has done in the creation of life that is truly phenomenal and takes our breath away. The amount of complexity, the chemistry that's going on there, it's really, it's why you begin to think that there was some flow of all that the universe has done to make it possible for such complexity to exist. Starting with a Big Bang in which the universe was almost formless, hot, without structure, to a tiny thing like this that has more complexity than a star. And it gives you an appreciation for things that are really quite simple that you see on Earth that are even more wondrous, and things that can't talk to us but tell us that something marvelous has been going on. So you can see this is I feel this is the most exciting direction for astronomy to go in the future. This is where our children and grandchildren will be spending a lot of their time if they're astronomers. And this is just the beginning of a big journey, whereas we're getting to the point where we'll see how galaxies form, and we're completing a century's worth of work to understand all these pieces that got to life. But in terms of life itself, we're just beginning this journey. And what a great thing to be at the threshold of it, and also to be in the generations that have the privilege of doing this after so many have wondered for so long. So we can celebrate that people in their cleverness and ambition and curiosity have brought us to this phase. And we hope that our will hold up to do these marvelous things. Thank you.